Off in chapter 15, looking at section 15.2. So here we're going to be talking about exponential and logistic modeling. Oh, thank you. Let me fix that real quick. That's a lot better, right? All right. One of the most common applications to both exponential and logistic modeling is describing populations. So let's start by talking about the exponential population model. So a population at time t, we represent as P of t, equals P naught, which is the initial population, times 1 plus R over 100. R is the rate of population change. So for growth, R is positive. For decay, R would be negative. And R is written as a percentage. That's why it's being divided by 100. And then to the power t, where t is some period of time. Notice that this is still like our general exponential model, right? Where P naught is A, and then 1 plus R over 100 is like our B, right? Still looks like A, B to the X. So everything we know about our whether things are growth or decay is still kind of the same. If that 1 plus R over 100 is greater than 1, it's growth. If it's less than 1, it's decay. So just looking at a quick example here. So this first one, P of t equals 12,587 times 1.0384 to the t. Is that growth or decay? Growth, because the b value is bigger than 1. And then it asks, what is the rate of growth or decay? So all we're going to do there is we're going to take this 1 plus R over 100, set it equal to 1.034, and then solve for R. Certainly. So to solve for R, I'm just going to subtract 1 and multiply by 100, and probably you can see that the R there is going to be 3.89%. Okay. If we do the same thing for B, is that growth or decay? Decay. So if we do the same thing, what do you notice is going to happen when we subtract the 1? We're going to get a negative result. And when we multiply through by 100, we get negative 1.33. So you can kind of phrase this two ways. So you can say the rate is negative the rate of population growth is negative 1.33. Or you can say the population decays at a rate of positive 1.33. So if you include the word decay in the name, you can drop the negative sign because the decay kind of takes the place of a negative sign there. If you don't use the word decay, you should include the negative sign to show that it is a decay situation. But that's just like a little bit of vocabulary or whatever. Not a big deal, but worth mentioning. All right, let's look at a situation where we're given a situation, just ask to write a model. So when we ask you to write a model, what are we asking for? I want to write the P of t function for that situation, right? The answer is not going to be a number, it's going to be an equation. So it says population model. So we have only one population model at hand. So we're going to say this. Now, our answer should have the the dependent variable and the independent variable should be in the answer, right? Our equation should have both those two things in there. So we just need to fill in the rest. So P naught is the initial value. Here we're told to determine the population model with an initial value of 15. So clearly P naught is 15. Increasing, so because I heard increasing, what do I know about the R? It's positive at a constant rate of 6% every year. So the R should just be 6 then. And then we have to make a decision because t is just time. So we need to pick a unit of time to use here. What unit of time should we be using in this? Yeah. Years. Why did you pick years? It says 6% every year. So we'll just write afterwards t is in years. And now we could simplify here a little bit, right? 1 plus 6 over 100. We just write that as 1.06. Again, if you're just typing this into your calculator, not a big deal. You don't need to simplify. But if we're asking for the model, typically we want to do that little bit of arithmetic there, right? We want like a reasonably simplified answer. Okay. What if we ask virtually the same question with one little catch here? So if I read this question, determine the population model with an initial value of 15, increasing at a constant rate of 6% every 6 months. What is the only difference here between this question and the previous one? That's every 6 months. Yeah, as opposed to every year. So we know initially we're going to do that much, right? Everybody's okay with me just scooting right here? The question now becomes the t is going to need a little adjustment, right? So what unit of time do we want to measure, or what do we want to use for t? There's kind of two obvious choices. One is not wrong or better than the other. Months, okay. You want to do t in months, okay. So how much of that compounding period is finished in 1 month? 1/6 of it, right? If it takes 6 months for one compounding period to occur, in 1 month, we would have done 1/6 of that. So instead of writing t, I'm going to write 1/6 t, or really I'll just write it as t over 6. The other obvious choice for a unit for time would be years. How many of compounding periods accomplish in 1 year? 2. So instead of writing t, we're going to write 2t. Both of these answers are correct. They're both fine. If you wanted to be a masochist, you could pick days or something, and then it's like kind of a nightmare, but it's fine. This is just to kind of illustrate to you how you have to adapt that exponent based on the unit. Or it's not wrong to just write, that's supposed to be a 5. That's a pretty crummy looking 5. And you could do something like that and just say t is in 6-month intervals and just, you know, any way of writing this is okay as long as you're kind of declaring what t is and you're making your adjustments, you know, to fit the unit of time that you've chosen. So again, if in the homework you're asked to do this, there's probably not going to be unlimited answers to check with. It may just have one of them or one of the possible answers, but something like that would have many, many possible answers. It just would have to be adjusting that exponent so that it fits the unit of time you've chosen to use. All right, let's do another one of these. So here it says, suppose that a colony of bacteria, of 120 bacteria, is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So when I read a problem like this to me sounds like a 2-step problem. Step 1, I'm going to have to write the model. And I'll just call that P of t for the sake of giving it a name. And in step 2, we're going to have to solve P of t equal to 400,000. Everybody's okay with how I interpret that from the words that were going on there? Okay. If you have questions, just holler them out at me if it doesn't seem, if I'm going too fast, or if you have a whatever, you know, just let me know. Okay, so let's start by writing our population model. So what should be our initial population, our P naught? 120. What should be our value for R here? So, okay, so why did you pick 50? So we want doubling. Okay, so let's just think about it for a minute, all right? Because maybe it's not entirely obvious. Let's say we have 10 as our start. If I'm doubling that, I want to end up with 20, right? Okay, so if I take 10 and I multiply it by 1 plus 50 over 100, that's multiplying it by 1.5. That would give me 15. If I took 10 and multiplied it by 1 plus 200 over 100, that's 3. That would give me 30. That's not right either. What does R have to be? 100. A 100% change is going to mean that at the end, the net change is doubling, right? So if I had something that cost $10 and we had a 100% price increase, it's gone up another $10 to be $20, right? So R is 100. And notice when we simplify that, 1 plus 100 over 100 gives us 2, which is our doubling, right? Which is what we want it to look like. So that I feel good about that. And then we have to pick a unit of time to use here. What unit of time would probably make the most sense for this situation? I would say hours as well. So what should my exponent be then? if we get that doubling every 3 hours, how much of the doubling is happening in 1 hour? Yeah, a third of it. So t over 3. Excellent. And if you want, we can simplify this down. As I said before, we noted that 1 plus 100 over 100 is just 2. So that's my step 1. Step 2 is we want to solve that P of t equal to 400,000. So we probably have 2 good ways to do this, right? The first way was what we talked about last time, which would be to graph the situation on our calculator and just find the intersection. But we did Algebra 2 last year. What's the other way we could use to solve this situation? We could use a logarithm. Okay? I'm going to do the calculator here real quick, and then we'll do the logarithm algebraically afterwards. Either is fine for right now, since we haven't introduced what a logarithm is, but like, let's not be coy. I know you guys know what they are. At least a little bit. You don't have to pretend to be experts still, but we'll go over it all again. If you're like, yo, I don't feel good about logarithms, that's okay. Then just do the graphing. No big deal. We'll redo logs in another section or 2. So I just typed in the left-hand side of my equation, that's P of t, and the right-hand side of my equation in 400,000 is y1 and y2. I'm going to set a window. I don't really know. I know that x is representing time, so 0 would be a good minimum. I don't know how long this is going to take. It feels like it's going to be a long time, so maybe 100 seems good. 200 per, like doubling, that's pretty fast. So I don't expect it to be like 5 million or something, but it's going to take a minute. Y is the population. The minimum population is 120, and we need to go up north of 400,000. So I'm just going to go 0 to like 500,000. Feels like some nice round numbers to me. And then let's just hit the graph and take a look at what we got here. So there's my pop. Whoa. That's growing fast. That is a steep population curve. Those bacteria are really getting down. To find the intersection, we'll just press second and trace, select the intersect command. Since I only have 2 curves stated, I can just press enter 3 times. We don't have to think about it at all. And we get about 35.11 hours. Does that feel okay to use, guys? Alternatively, if I wanted to do this algebraically, that's totally okay. What would the first step I need to do if I wanted to solve this algebraically? Well, if I'm solving something algebraically, I want to undo the order of operations. So I'm kind of working in the reverse order in my undoing. So first thing I'd want to undo is any addition or subtraction. Well, there's none of that. Then I'd want to be undoing any multiplication or division. So the first step would be to get rid of that times 120. So I would divide both sides by 120. And I know this can all reduce, but it's all going in the calculator at some point anyway. So I'm just going to leave it all and not burst my brain cells trying to reduce fractions at 8:11 in the morning on a Wednesday. So I'll just leave that the way it is. The next thing I need to do then is I need to somehow get rid of this exponent base of 2. To do that, we need to use a logarithm. Now, there's lots of different types of logarithm bases. which base should I choose for the logarithm in this case? 2. Excellent. I'd want the logarithm base to match the exponent base. Now, you don't need that to do this, but boy, it makes life a whole lot simpler if you just do that. So I just want to be clear about this, that you can use any log in this case. That's not wrong to do that, but it is not real efficient. And, well, my life is hard enough. I don't need to go making things more complicated than it has to be. I'm just going to make good choices and expect good things to happen. So that's that. And the last step then would be just multiply by 3. And I'm going to write it out front like this so that I don't get confused about whether that 3 is multiplying inside my logarithm or outside my logarithm. I try to treat it very much like a square root, where I try to put all this stuff in front so I don't accidentally get confused about where I'm doing it. And then it's just calculator time. So I'm going to do 3 times. And then to type in a log with a different base like this, we press the math button and scroll all the way down near the bottom and pick the log base command. That'll let me go and type in whatever base I'd like there. And then I'll just do 400,000 divided by 120 and press enter. And I get that exact same 35.11 answer that we saw before. Again, no preference from me which way you'd want to do something like this. Either is fine. If you feel comfortable using the logarithms, I think that's great practice. This solving method, or the graphing method, though, is a nice one to at least be comfortable using, particularly in like a standardized test situation where it's like, I'm not really sure I know how to solve this equation. Well, it doesn't matter. I'm just going to graph and find the intersection. And that's okay, because they don't care about my work. All they care about is the right letter getting filled in on the standardized test. If you have an ACT or an SAT and you run into something that's like, ooh, I'm not sure how to solve that, just graph it and find the intersection. It's a really nice, effective method that you have available to you with a state-of-the-art graphing calculator. They're really not that state-of-the-art. They're pretty old generation technology. The next thing I want to talk about, another situation where we can use this same population model that we've been talking about, is dealing with radioactive decay. Do you guys talk about this in your chemistry class at all? Okay. So the idea is, so you have elements, right? And an element is defined by the number of protons it has. And we know that there's different kinds or different versions of the same element. We call those isotopes because they have a different number of neutrons attached to them, right? Depending on the number of neutrons attached to the element, may become unstable and want to get rid of some of its atomic material to move to a lower energy state. That process is called radioactive decay, where an atom releases some of its atomic material. And one of the types of radiation that happens, an element just turns into another element. So like plutonium is really radioactive. They use that inside of some nuclear reactors. Plutonium decays down eventually into lead. It goes through a bunch of different elements on its way, but eventually ends up as just like lead. Now it takes like thousands of years to, for it all to turn into lead, because it's a really slow process. So the way we measure that really slow process is with something called a half-life. So the half-life is the amount of time it takes for a sample of that radioactive element to decay into something else. So we measure half-life typically in some unit of time. Some elements are really unstable and it doesn't take very long. Your half-life might be measured in hours or even seconds for some like really special like man-made elements. But oftentimes they could be like thousands of years in other cases. So it just kind of depends on the element, what that half-life is going to be measured in. But some of them are really long. So the key here for us, when we talk about half-life, is that the R is then going to be negative 50%. So that's the key for us in taking our existing population model and using it to do one of these half-life problems. So again, we know it's radioactive decay. That's why we're getting the negative sign, is because of the word decay. And we, as we talked about before, doubling was 100%. So halving should be 50%, right? If you go to the store and something is half off, it's on sale for 50%, right? All right. So let's do a numeric example here. And be on our way. All right, suppose that the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram of remaining. Again, I see a two-step problem, right? Write the model, and then solve the model equal to 1. So step 1, P of t equals, the initial value is going to be the amount of substance we had at the start, which in this case is 10, right? Because it's radioactive decay, I know that the R is 500, or is 50, 500. And when I say 50, I mean negative 50. Obviously, I didn't write that. And then we need to pick a unit of time here. What unit feels like a good unit for time? What do you guys want to do? Days feels natural, right? It says days in there. So we'd write that as T over 35, because in 1 day you've accomplished 1/35 of your half-life. In step 2 then, we're just going to take P of t, set it equal to 1, and solve. I'm just going to do this on the calculator here rather than with a logarithm. We demonstrated how to do that once. That's fine. It should be relatively familiar. We'll do it more again when we talk about logarithms in earnest, but it's a little bit, Mr. Kulik, jumping the shark. But I know you guys have seen these before, so I don't want to pretend like I don't want you to do it. It's a perfectly reasonable method to be using here. So I'm just going to go ahead and type in my model. Into Y1, into Y2, I'm going to type in 1. And I'm going to set a window here. So the tough one for me is the X max, right? So let's think about this for a second. We start off at 10, right? And in 1 half-life, we go down to 5. Second half-life to 2.5. Third half-life to 1.25. Fourth half-life, we're going to get sub 1. So I want at least 4 half-lives worth on my x-axis. So that's 35 times 4, which is like 140. So I'm going to do like I'm just going to round up to an even or like a rounder number and do 150. Is kind of what I'm doing just in my head. I'm just kind of doing a quick little heuristic to get a nice upper bound for that. Now the Y scale is really easy. Since it's decay, I know eventually it's going down to 0, so the Y min will always be a 0. And the Y max is just going to be the initial amount, because that's the biggest it's ever going to be. So just 0 to 10 on the y's. Those should be easy to set, since we know we have a lower bound to the function and we have a starting point. So there's my function and my intersection. So second, trace, choose the intersect command, enter 3 times, and I get about 116.3 days. Now, alternatively, if you had done P of t equals 10 to the 1/2 t, where t is in half-lives, and we do the same thing, in the calculator, so just go ahead and make that quick little adjustment. Boop, 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 boop. Oops, need the x. So if I hit graph again, look at what happened. It's way over here, right? It's fine, it's a crummy picture, but it's the intersection's there. So just enter, enter, enter. I get 3.32. And if that's half-lives, right? So if I multiply that then by 35, I get the 116.3 days, the same as the other problem. I just want to point out too, if you chose to do a different unit, if we want our answers in time, it's asking how long, or find the time. Typically, I would tell you the unit of time that I want my answer in, like how long in days does it take. So again, you could set it up with the t over 35 and your answer is your answer. If you forget how to do that or weren't sure, you can always get your answer in half-lives and then just multiply, right? It's not a big deal. Okay. Now, here's the issue though. If I take one of these population models and it's a growth situation, it can eventually give me a really unrealistic answer, right? Hi, Alexis. How are you? Living the dream here?
Always.
Zoe Hope. It's your get out of jail free card. Well, later card anyways.
Thank you.
You're welcome. All right. So one of the reasons is eventually a population is going to run out of room or resources or become so, yes, of course, or become so populous that it makes it like easy for predators to get at it, or you run out of food or whatever. These exponential population models aren't often a good fit in reality. Instead, what we want to do is have something where when the population is small, we grow exponentially. But as the population starts getting bigger, that exponential curve kind of levels off and has like a natural upper bound to it. The typical choice for this kind of an equation is a logistic model. And we talked a little bit about the logistic model last time. So let's look at an example here where we use a logistic model. So you start a bunny petting zoo. You determine that the population of bunnies on your farm can be modeled by the equation b of t equals 800 over 1 plus 99e to the negative 0.5t, where t is measured in years. And we're asked then a series of questions here. How many bunnies do we have initially? So what value of time does initially mean? Zero, that's correct. So if I just do p of 0, I'm just plugging 0 into this function. Now, negative 0.5 times 0 is 0, right? E to the 0 is 1. So 99 times 1 is 99, and 1 plus 99 is 100. So should have 8 bunnies initially. Everybody's cool with that. Pretty easy, right? All we're doing is plugging something into a function, evaluating. Whoop-de-doo! Mr. Coolett, could I type that into the y equals menu and just evaluate it on my calculator doing like y1 of 0? Yeah, dude, definitely. Not wrong to do that. Part B says, what is the maximum sustainable population of bunnies on your farm? So if you remember from last time when we talked about logistic curves have 2 horizontal asymptotes. They have one at y equals 0 and then one at y equals c, where c is the numerator of the function. So in this case, since it's growth, that c is the upper bound. So that's our maximum sustainable population. It's just the upper bound, the horizontal asymptote for our logistic. So I got that from not doing anything at all. I just had to remember how to find those horizontal asymptotes for the logistic and then look at the function, right? I didn't do any calculation and plug anything in. I just kind of looked at the number and said, oh, that's the upper bound. C then says, how long will it take to have 500 bunnies? So I'm going to solve B of t equals 500. So again, we can do this with our calculator. Here I would definitely want to use that fraction command because the parentheses are going to get a little bit overwhelming. So that to get to that fraction again, command again is alpha, and then y equals is the shortcut. You pick the first fraction option. We'll give you the like numerator over denominator style that you want. Again, I don't know what what this is going to take, but this is measuring in years. We're starting at 8. We want to end up at 500. I don't know how long that's going to be. Let's say 50 years. I'm just taking a guess there as what a decent upper bound will be. I might have really overshot it, but I'd rather overshot it than undershoot it. You know what I mean? Bunnies are kind of notorious for reproducing quickly. I know the horizontal asymptotes for this logistic function are 0 and 800, so that's going to be good for my y min and y max. And then I'm just going to hit graph. Oh, I did overshoot the x a little bit. That's okay. Again, all we really need is that intersection. And again, I'd rather have it maybe too many x's than not enough x's. So I get about 10.21 years. Just for grins, let's also solve this algebraically. So what do you want to do as our first step if I want to solve this algebraically? I'd want to get that variable out of the denominator, right? So lots of different ways you can think about it, but cross multiplication feels pretty natural in this case, where I can just think about it as two fractions equal to each other. Now it just looks like our normal exponential equation, so that's good. I'll just start by dividing both sides by 500. And I'm going to just reduce that fraction to 8/5 because, well, that's easy reducing to do. I just get rid of some zeros. And then we need to subtract 1 from both sides. So you could write that as -1, or I'm just going to subtract the 1 and just leave it as a fraction there. It's all going into our calculator eventually, so it's not a big deal if you just want to roll with writing the workout and not dealing with the fractions. But next stop, I got to divide by 99. Well, that's not a lot of fun. So I'm just going to write that as like that. Just thinking about multiplying by 1 over 99 instead of dividing by 99. Since I had the fraction on the other side, it's a little bit more convenient to me to think about multiplying as a reciprocal. Now, I recognize that can reduce, but like I'm just not that interested in it because it all has to go into the calculator anyways. And the reducing is, while trivial, like doesn't make it any shorter for me to write. So I'm just not really too interested in it. Next thing I got to do is get rid of that exponent base of e. To do that, what do I need to use? A logarithm, specifically the natural log, because natural log is log base e. So I'll do that to both sides. And again, as we said before, any log here would do, but it makes the simplification becomes a little bit more of a hassle if you use a different logarithm that doesn't match the base of your exponential. So like save yourself the trouble, just match the bases. And the last step is I just need to divide by -0.5, or I'm just going to think about it as multiplying by -2. And again, I get that same 10.21-ish. We feel okay? Yes, of course. Yeah, no problem. And just to be clear, you don't need to be using one method or the other here. Either is okay. You could use them interchangeably at this point. Let's not pretend like we don't know what a logarithm is. You're more than welcome to do that. If you're like, I think I'm going to wait till we go over it, like logs again, before I start using them, that is totally okay. You can definitely do graphing for these story problems. And that would be okay even through the test, right? But we're going to start talking about logarithmic functions here today. Do you guys remember what the definition for a logarithm is? Okay. Well, it's just that these two equations are equivalent. B to the y equals x is equivalent to log base b of x is equal to y. That's our definition for a logarithm. It's just this statement that these two equations are equivalent, that I can take any exponential equation, recast it as a logarithmic equation, or take any logarithmic equation and recast it as an exponential equation. Does that ring a bell looking at it? Good, 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 good. Let's just take a minute and go back and evaluate some logarithmic expressions. Now I realize each one of these you could type in your calculator. Let's not do that though. Let's do these by hand just to kind of illustrate what is going on and to reinforce this logarithmic relationship we just kind of discussed. So there's kind of two ways to approach this. The first way would be to think about this as like, say that thing is equal to a, so I could rewrite this as an exponential equation. And then from there, it's probably pretty easy to see that because 16 is 4 squared, a just has to equal 2, right? You guys recognize that? Where all I did was use that exponential part of the definition to rewrite that logarithmic equation as an exponential. The other way that you could think about this, though, is you could attempt to rewrite 16 as a base 4 number. Well, I know that 16 is the same as 4 squared, and I know log base 4 is going to cancel with exponent base 4 and give me 2. That's equivalent to doing the same thing that we just did. We just did it in the logarithmic form instead of the exponential form. Either sets of work is okay. I think about it the second way is typically the way I think about these problems, but if they get real complicated, it's often going to be easier potentially to deal with it in the exponential form. But let's keep on going. So what am I going to do with b here? Well, I can either write it as 5 to the b equals the square root of 5. What can I do with that? I need to rewrite square root 5 as a power of 5, right? What power of 5 is equal to the square root of 5? 5 to the 1/2. Excellent. So then we can see that, okay, well, b just has to equal 1/2. Okay, we do the same thing. We have 3 to the c equals 1 to the 27th, or 1 over 27, 1 to the 27th. 1 over 27. So here, I need to rewrite 1 over 27 as a power of 3, right? So, well, I know that 27 to the negative 1 is the same thing as 1 over 27, right? That the negative 1 exponent just makes a reciprocal. And I recognize that 27 is 3 to the 3rd. And when I have an exponent of an exponent, how do I simplify that? They multiply, right? So then I can see, well, okay, well, c had to be negative 3. Is everybody feeling a-okay so far? So here, the next one, we have log base 12 of 1 is equal to d. So we'd say 12 to the d is equal to 1. Yep, so Prater says that anything to the 0 power is 1 other than 0. So we can certainly write 12 to the 0 as 1. So d is just 0. As a reminder, 0 to the 0 is equal to It's not 1. It's not 0. It's not undefined. It's called indeterminate, which means that depending on the situation that you're looking at, it could take on a variety of different values, which is like kind of the nightmare. If you take AP Calculus next year, we'll talk more about indeterminate forms and how to deal with them. It's like a whole thing that we deal with. It's really fun. It's actually not bad at all. ABCD. This is E then. So we'll say 8 to the E is equal to 8. Well, that's pretty easy, right? Well, E is just 1. So conclusions. Any log of 1 is 0. Any log of itself is 1. Any log is going to be positive if the argument is greater than the base. And is going to be negative if it's less than the base. That's not right. Should be that. That's what I meant. Right, because any log of 1 is 0, right? So you can certainly should have a positive log if you're like 1.1, which would be decrease anyways. All right, so that's the takeaway there. Couple of little vocabulary pieces. I think we've talked about each of these already. There's 2 special logarithms that get their own name. They are the common log, which we just write log with no base written in, that we assume the base to be 10. And then there's the natural logarithm that we write ln. That's where we assume the log base to be e. So let's just run through a couple of quick simplifying examples using the common and natural logs. All right, first one should be, can we do this in our head? Braden says 3, that's correct, because 1,000 is just 10 to the third. The next one should be 1/5, because the 5th root of 10 is just 10 to the 1 over, or to 10 to the 1/5. How about this one? What if I point out to you that that's 1 over 100? It should be -2. What about D? Exponent base e cancels the log base e. You're left with just 5. Oh, yeah. How about E? An exponent base 10 will cancel the log base 10. So x should be 10 squared, or 100. How about this one? What should y be then? What's going to cancel the natural log? Exponent base e. So we should have e to the 5th. God bless you. That was a loud one. Everybody feel okay doing this? We kind of remember doing logs last year. I know that this is, I think of the Algebra 2 topics, traditionally this tends to be the hardest thing you do in the Algebra 2 class is the log stuff, but you guys seem to have a good memory of what you did. So we want to talk next about some special properties of logarithms. So there's 4 major properties of logs. There's the product, quotient, power, and then change of base formulas. Now the first 3, the product, quotient, and power properties, are important. We'll use those frequently throughout the rest of this chapter. Those are ones you definitely need, and we'll use a ton. The change of base formula is no longer very relevant for you, mostly because of the kind of calculator you have available to you. So when Mr. Kulik was in high school, and you had to do like log base 3 of 10, we did not have a calculator with a logarithm on it. You had to use the change of base formula to rewrite that as like, log of 10 over log 3. Go to the back of the textbook that had a table of logarithms in it. Look up what the number for log base 10 or log of 10 and log of 3 was. Type those numbers into your calculator and do the division. Which sounds like a nightmare, right? That's what math looked like. Now, eventually we had scientific calculators. That happened before the end of high school that had like regular log or natural log built into them, and you could use those, and then you could just do the change of base formula on your calculator. But not until I had a graphing calculator was I able to do like pick my own base for a logarithm. Now I think on the scientific calculators you have now that's an option. But it was not a common option when I was a high schooler. We absolutely used the change of base formula all the time. You guys really don't need to use it because you can just do the log of whatever on your calculator. But that's absolutely what that looked like. How much fun does that sound? Did you guys prove these things in Algebra 2? Do you remember? I don't think so. Let's do it now. At least one of them. I think I have some of the other ones are assigned as homework. So we're just going to do the product property here. So what we want to show in the proof is that log base b of rs is equal to log base b of r plus log base b of s. So what I'm going to do is I'm going to say, okay, I'm going to define r or x to be log base b of r and y to be log base b of s. And then use my exponent property to say that this is the same thing as b to the x is equal to r, and this is b to the y is equal to s. So I'm just using the definition of a logarithm to make that conversion. Everybody's okay there? Then I'm just going to multiply these two equations together. What's b to the x times b to the y simplify down to? B to the x plus y. So I'm just using the product property for exponents to do that. And now what I'm going to do is I'm just going to do log base b to both sides. Log base b cancels exponent base b. And I remember that x was just log base b of r, and y was just log base b of s. That's what I wanted. So the key here was this step, right? Is I just took my logarithms, converted into exponential form. Go ahead, Giselle. That's okay. And then used my property of exponent, the product property of exponents, to do what I needed, and then just took the log of both sides and boom, boom, boom. The process to solve the other two, the quotient property and the power property, is the same. So you'll rewrite your logs as exponentials, multiply or divide them as needed, use the corresponding property of exponents, and then take the log of both sides and boom, boom, boom. Okay. I think that we ask you to prove the other ones in your in the homework. So there's two types of problems that we'll ask you to do that use these properties. So the first type is expanding. To expand a logarithm, you're going to start with a single logarithm and rewrite it as the sum or difference of many logarithms. When we do that, we look for the quotient property first, the product property next, and the power property last, unless there's like a set of parentheses that kind of imply that, you know, like we should do this exponent, like there's a parenthesis with an exponent around a division thing, where it's like, okay, order of operations is telling me not to do it that order, but that's the idea. Okay. So here's some quick examples of doing this. I think after we work these examples, it's probably our stopping point for the day. We'll finish up logs next time, but that's not a big deal. So the first thing I'd look for is quotient. Is there anything multiply or dividing in here? No, no quotient property. Next thing we do is look for a product property. Is there anything being multiplied in there? Yeah, where's the multiplication symbol at? Between the 4 and the x, right? So I can use the product property to rewrite this as log base 3 of 4 times log, or plus log base 3 of x. Now we start over. Inside of each of these logarithms, do you see a quotient? No. Inside of each of these logarithms, do you see a product? Okay, where do you see a product? Rita? What? Okay. Oh yeah, not yet. Do we see a power inside of any of these? Well, you kind of should have seen either a product or a power. 4, you could have thought as 2 times 2 or 2 squared. Either way of thinking about it is fine. Thinking about it as a power is the better option, though, because it's going to be less simplification. So there is a hidden power property there. Be careful, don't put it past Mr. Kulik to use non-primes and expect you to notice that there's a product or a power property hiding on you. Okay, I'm a sneaky jerk. I'll definitely do that. And at that point, we know we're done, right? There's nothing we could do with the x. The 2 is now prime, so there's nothing to do with that. We're good to go there. The next one here, again, we start with a quotient. Any quotient going on? No. Next thing we look for is product. Do you see a product property? How many product properties? 2, because there's 2 multiplication symbols, right? So there's a multiplication between the 3 and the A and between the A and the B. So if I use the product property twice, I could do that. Again, now I'm going to start all over with each of these logs. Log of 3, quotient? No. Product? No. Power? Okay, that one didn't change. Next one, log A, quotient, power, product. I said them in the wrong order. Last one, log of b to the 5th, quotient, product, power, yes. And then I should check log of b to make sure there's nothing else going on there, but clearly there's not. It's a monomial, or it's a monic variable or whatever. Feel okay still? Last one. Okay. Quotient. Yes. So the quotient is numerator, or log of the numerator, minus log of the denominator. So if I look at log of 2x, is there a quotient there? No. Product there? Yes, right? Between the 2 and the x. So I can apply the product property to that. And then if I look at log of square root x cubed minus 3, is there a quotient in that? No. Is there a product in that? Is there a power in that? Okay, what is the power? The 1/2 for the square root. Okay. All right. So log of 2 and log of x are both done, right? There's nothing more to do there. Can I do anything more with x cubed minus 5? Is there a power property there? I see an exponent, but there's not a power property there, correct. So if there was, what it would have to look like would have to be like that, and then you'd have a power property. But if you have a polynomial, it can have exponents on it, and there could be no power property going on unless the exponent applies to the entire piece. Everybody feel okay? All right. This is where we'll stop. At this point, you guys should be able to do 17 through 82. I know, but here's the thing, guys. Like, a bunch of these are like evaluate without a calculator, log of 4. You know, like it's a bunch of stuff like, or even like use the change of base formula in your calculator to evaluate log base 5 of 12 or something, where it's like, I'm only going to do is type in my calculator. Like there's a lot of like 15-second problems in here. So like there's a lot of numbers there, but like it's not a lot of work. Okay. I know, you don't trust me. I understand. Anyways, we'll pick this up next time. Have a good day. Good luck on your future exams. Do we still have exams going on? There's some people still taking stuff. Yikes. All right.